All right, we are at chapter 24, electric potential, and we're going to start with section 24.1, electric potential and potential difference. So let's share the PowerPoint. And there we go. And they show a lightning storm, and the potential difference between the cloud layer and the Earth can be hundreds of thousands of volts. Now, you've heard of volts. You know that your household electricity is 120 volts. If you have an a large electric uh, appliance like a dryer, it runs at 240 volts, which is twice the 120 volts. And we'll get to that when we get to household um, circuitry. I forget what chapter it is. It's one of the future chapters. But let's go ahead and uh, look here. You have a setup here that's basically a parallel parallel plates that form a uniform electric field. You should have seen a uniform electric field when you did your experiment. Um, I forget what the experiment was. Experiment 22, the equal potential surfaces. When you did that experiment, you should have seen that the electric field was uniform between the two um, elect the two grids on your piece of paper. So what happens if we have this electric field from these plates, and you put a positive charge in there? Well, work is done. The the charge, it's a positive charge, so it's going to be repelled by the positive plate, and it's going to be attracted to the negative plate. So whenever you have movement, you have work done. So the work is equal to the electric force times ds, the whatever um, length that moves. Well, the electric force is equal to q, the charge q times the electric field. So it's the electric force times ds is QE dot ds. And recall from the internal work is the negative change in potential energy of the system. The internal work, if you recall, the internal work done in a gravitational system is the negative of the change in gravitational potential energy of the system. So we have a similar case here. So the du is equal to negative uh, internal work, which is equal to minus QE dot ds. So we're look at the change in electric potential is equal to minus Q times the integral from A to B of E dot ds. And we're going to define the potential divided by Q, the potential energy divided by Q is as volts, as V. So you can see volts, U is the potential energy, and Q is a charge coulombs. The potential energy, of course, is in joules. So volts is going to be joules in coulomb, joules per coulomb, and we'll see that in the next slide. Okay, we've got the same figure here. The parallel plate, basically, it's a capacitor. We'll learn about this, and I think it's the next chapter. So the delta V is equal to the change in potential energy divided by the charge, and that's equal to negative the integral of E dot ds. And this is going to be a path integral. And we'll discover that since it's a conservative field, the path doesn't matter. That's why we have equal potential surfaces. But we'll get to that later. So the work is equal to the charge times delta V, Q dot delta V. So if volts are joules per coulomb and you're multiplying it by coulombs, you're going to get joules, which is what work is in. So 1 volt equals 1 joule per coulomb. That triple line, that equal sign with a triple means it's defined. So 1 volt is defined as 1 joule per coulomb. And 1 Newton per Coulomb is equal to 1 volt per meter. Well, what do we get newtons per Coulomb? That's from our electric field. So the electric field can also be expressed as volts per meter. And that makes sense. I mean, as we, if you have an electric field, it's real strong. It's going to be X number of volts right next to the plate. And as you move away in meters or centimeters or millimeters, it's going to decrease. Okay, so the electric field is a measure of the rate of change of the electric potential with respect to position. The electric field is a measure of the rate of change of the electric potential with respect to position. Now here we show it looks like a dental technician taking an X-ray of of someone's mouth, and the energy coming out of the X-ray is expressed in electron volts, and 1 electron volt is equal to 1.6 times 10 to the minus 19 coulombs times volts. It's an electron volt. So you've got, what is the charge on an electron? It's 1.60218 times 10 to the minus 19 coulombs. And of course you have 1 volt. And if a volt is joules per coulomb and you multiply by coulombs, you're going to get joules. So 1 electron volt is equal to 1.60218 times 10 to the minus 19 joules. Okay, let's, is that all there is to that? I thought there was more to that. I guess not. Okay, here are some, in this figure, 2 points A and B are located within a region in which there is an electric field. How would you describe the potential difference, delta V, from B to A? Well, if the electric field is emanating outward, the electric field is greater at A than it is at B. So VB being smaller minus VA being larger, the result is negative. It is negative. So VB minus VA, the potential difference is negative. All right. Now, in the figure, 2 points A and B are located within a region in which there is an electric field. How would you describe the change in potential energy of the charge field system for this process? Well, in this case, it's positive, because delta, the change in potential energy, delta U, is equal to Q0 dot delta Q0 dot delta V. So if a negative test charge is moved through a negative potential difference, the change in potential energy is positive. Okay, so it is positive. And that's it for the, I think, yeah, that slide is for 24.2. So we'll stop it here.